Welcome back. So until this point, we have been looking at very, very fundamental algorithms, but algorithms that we consider to be uninformed. There's a really, really key element of search that we have not yet discovered. So in this video, we're going to be looking at greedy best first search, which I think is a really nice algorithm just to exemplify what we're missing from search problems, how we're going to add in additional information, and then hopefully move towards these really advanced, these really state-of-the-art search algorithms that exhibit substantially better practical performance than the algorithms we've been discussing up until this point. There are, of course, always different strengths and weaknesses of each of these algorithms, and all of them have their own place in our giant web of search algorithms and problem domains, and they are all better in some problems versus others. But we'll start to see that these uninformed algorithms are missing something key. So, you know, BFS and UCS, I'll show an example of their search behavior here, but what we're seeing really is that they are, by default, these algorithms just expand almost radially outwards. They're conducting a search strategy that is completely independent from the actual problem you're solving. If you drop me in the maze and I'm trying to go from some start location in a grid to a goal location in a grid, I, as a human, I know which direction I probably want to be going in. What we're not seeing in these search behaviors previously is any form of idea of where they're going. They are essentially searching blind. We call this uninformed. So what we're moving towards is this idea of informed algorithms. So a search algorithm is informed if it relies on problem-specific knowledge. That helps to decide which node to expand next. And that is the root of the issue. Up until now, we had a start location, we had a goal location. The way we've been looking at these algorithms progress through the tree, which node they choose to expand, is completely uninformed about the correct direction towards the goal. This is the idea, right? That we were not yet looking at problem-specific information. We are given a problem when we're searching, right? We have a goal or multiple goal locations that you want to reach. We can reason over this as humans and as computer scientists in order to inform us and to make better decisions in this world. So greedy best first search it's an algorithm that's going to exemplify this quite succinctly, I think. So the search strategy for greedy best first search is only very slightly different. We are going to expand nodes greedily based on an evaluation function, which we're going to call f of n this time, rather than the path cost g of n. So expand nodes in order of an evaluation function, which we will call f of n. So for any node n in the graph, similarly to g of n, we will define some form of function, which we'll talk about plenty in this video and in the next. We're going to be using that instead to rank our nodes in our priority queue. So we'll again have a priority queue. So I'll write that here just as well. So it's the same thing, we have a priority queue, but we're going to be ranking this by f of n this time. Now I just want to walk through a very simple way to make an evaluation function. This is all going to be moving towards the idea of heuristics. Now this may or may not be a familiar term to you at all, But what the entire field of study really is called is heuristic search. So heuristics are going to be extremely important, but I'm going to spend an entire video talking about them in the next video. So join me there for that main discussion. In this video, I'm going to hopefully share with you an intuitive idea of where these come from and essentially how can we define a function that is going to inform search. So let's look at this example then. So we have a very standard grid. We spawn a start location, we have a goal location. Well, for every node n, we need to define a number that's going to tell us, that's going to help us rank nodes, rank where we want to go. Well, one really natural way, I think, in a grid is to rank nodes by how close they are to the goal, right? Like we want to go to the goal. So what we're going to see then is that the distance from G to G is going to be 0. But what we're going to do then is to describe how that changes everywhere else. So first, we are going to look at all the nodes right next to the goal. I'm going to just say we can only move north, east, south, and west just for this example, just to make it easy with ignoring diagonals. Yeah, so each of these are only one move away from the goal, right? You'll see then that this node here, well, this is, you're going to have to step once in either direction and again to get to the goal. So these all have a cost of 2. Similarly, in the straight directions, these would also need 2 steps to arrive at the goal. I'm just going to expand outwards, right? And you kind of see that this information somewhat propagates away. So this would also need 1, 2, 3, 4. So these are 4, and then these are our 3 still. And I'll fast forward this bit really quickly. Okay, and so what I've done here now is propagated the information outwards. This is not a 5, this is the start and goal location, which I've drawn circles around to try to distinguish them. So this is S, right? And so this is quite interesting, right? We now have a number to represent an evaluation of every node in its relation to the problem-specific knowledge of where the goal is. So we are going to use this in order to inform the direction search progresses in and how to move in a recommended direction. So for greedy best first search, this is really, I think, the easiest one because we are solely basing the next node to expand based on these numbers. So it's a really easy visual explanation of how these heuristic or evaluation functions are going to work. Okay, so let's have a go then at drawing out the search tree behavior, similar to the other algorithms we had a look at. So of course, we begin at the root node, S. Now, we're in a grid, we're allowed to move 4 directions, as we've talked about. So there will be 4 children here. Simply because I don't have them all like happily numbered like we've had in the past, right? A, B, C, D, E, F, G. I'm going to just write in the numbers because it's going to be a very simple example. So see how if we move north, we get to a 5 cost and vice versa. So we have 3 5s, and then we also have 1 3 if we were to move east. So now we are essentially, well, all of these, of course, we have our open list initially. Open just has S. We pop in S to add in these other nodes. Again, I'll just write in the numbers, but we have one with 3, 5, 5, 5. So the next one we're going to expand based on it was ranked, its evaluation function, f of n, gave us a better estimate of the distance to go, we'll call it. It's the best node. It's the best node based on some evaluation function. So we're going to greedily choose the best first. So we're going to expand this node here. What that means is that, right, these will have dot, dot, dots. These are all the other nodes it could have generated, but we're expanding this node here. I guess I'll circle them to help us follow what's happening. This one then is going to find another 4 things it can move to, right? Well, it could move back to another 5. It can move to a 4. It can move to another 4. And it can also move to a 2. So we have that the 2 sinks to the front. We have 2 4s. we hit our previous 3 5s, and we actually also have another 5. So all of these would be called different nodes. I'm just, you know, we could have given them all names like coordinate systems, right? You'd write the coordinate systems perhaps to dictate which of these states these correspond to. I'm just keeping it very, very simple here. Essentially, right, then of course we look at the 2, we expand the 2, we generate more, ... But what's actually happening is we generate a 1, we generate that again, and it has more dots of its own, but then we find the goal G. So best first search, greedy best first search, is expanding at every point in time the cheapest node in our open list based on some evaluation function f of n. The G value here, of course, was going to be ranked as 0, right? We didn't write that in because there was already a G, but then you would pop that and we'd return happy days. We found the goal, and we found the goal with the cost of how, you know, the depth of the node or the cost, however that's related. So yeah, greedy best first search is a really simple way to start thinking about this. We're moving towards this idea that we have informed algorithms. We know where the goal is. We should use that information to inform ourselves about how we want to interact with the world. This is a super simple example because we're very greedily choosing things based only on this evaluation function. I've given an example here where we're using what will be called the Manhattan distance, because Manhattan's essentially like a rectangular grid, but it's just that we're using the distance that you would have to step in a grid to the goal. If we were to talk about the properties of greedy best first search, we would see that it is actually complete on finite graphs. On infinite graphs, it can get lost. It's a greedy algorithm, right? Greedy algorithms very usually can just get lost, right? They can follow these cycles, they can go down these paths that they'll never be able to escape. So on an infinite graph, it is not complete. And then in either case, it is not optimal. It is not guaranteed to find the optimal solution because it has this really greedy nature to it. I'm not going to spend too much time on this now. I think comparative to our other algorithms which have like these nice guarantees, GBFS is mostly used to set up the evaluation function f of n that's going to be a really important part moving forward. In terms of the time and space complexity, it would be O of b to the m, where again m is the length of the longest branch, which is also quite bad. I think the key piece of the puzzle here that maybe you're not currently seeing right now, because when I draw it like this, everything looks happy, right? You're always going to move in the right direction. But as a bit of a segue into perhaps the next video on heuristics, note that these numbers are not always correct. Problems, or real-world problems, are always a little bit more substantially complicated than an empty grid with nothing in the way. So, as a small example, imagine if I added in some walls. So when I start to add in some walls, you'll see that these numbers, 5, 4, 2, these are no longer correct. We as humans see that there will have to be a longer detour around now. But the evaluation function we're using, however you choose to define this, again, is probably going to be some form of rule-based thing. They're not always correct. And so following things greedily can lead you astray. You can enter little corridors or rooms and get stuck in these cycles. The information provided by the evaluation is not always trustworthy, and we're going to have to reason over that and find interesting ways to develop search algorithms that can make use of this information, right? These problem-specific knowledge is still incredibly useful, but we really need to find a way to balance that with as well actually part of the search that we're progressing, not just greedily following the numbers down paths that will not make sense. So please join me then in the next video when we're going to take a deep dive into heuristic functions, which are a really, really integral part of search algorithms moving forward. And then we're going to move towards the fundamental pathfinding and heuristic search algorithm, the A-star algorithm. And that will, I think, be where your pathfinding journey really begins. So please join me there.